I sent yesterday the file from yesterday's presentation to Tiago. In any case, in this web page from our group in Madrid, you will have all the presentations there in PDF files that you can download. And also the codes that I will be using for the hands-on, probably on tomorrow or on Thursday, it will depend, will be there, okay? So, yesterday, I really dashed through quite a few things, and I think it would be worth to revisit some of them before going further. So let's recall a few things that we said yesterday. Yesterday we took a look at how Schrödinger's equation for the scattering looked like for a single particle, right? This was actually the expression, and if this is, can you see the pointer? Right. This is the expression where you do actually perform the expansion within the Schrödinger's equation using the advanced green function, which is nothing but the spherical wave, right? And within Born approximation, this will be truncated at the linear level, neglecting square terms in the potential, right? So this is one of the conditions. We are assuming that we will be dealing with weak potentials, and also the extension of the scattering length, extension of the potential, is relatively small compared with the incident wavelength. So this is called the adiabatic approximation, right? With this, we end up with the equation that we will be using, where we have the scattering radiation that has the incoming wave, this is a plane wave, plus this integral over the spherical wave with the interaction potential here. Well, this part comes out as another spherical wave with this term that is the scattering amplitude that we'll be dealing with constantly also all these talks, right? We can express it finally in terms of the potential itself, not the simplifying form. Recall that this contains the factor, the square of the particle, plus these terms. In the case of the scattering of photons, this expression has to be renormalized because we don't have mass. We will have to use a different expression because all the equations look different, and we will have to use Dirac's equation instead of Schrödinger equation. Right? So the point is that within this Born approximation, we will neglect all these multiple scatterings in the area where the potential has some relevance. So we will have, in reality, multiple scatterings in this way. That means that the particle is scattered by one point. Recall here, for instance, would be our scatterer, our atom. But this would be the area of influence. For instance, if you have scattering of X-rays or light, or simple light, visible light. So in the case of the nucleus, things are slightly different and simpler because they act as delta functions. So here we might have scattering within the same atom, so to speak. This is in principle neglected. So we only have one single source of the scattering, right? With this, I show you how you end up with a simple expression for a Yukawa potential. That is perhaps the simplest thing that you can actually use for integration. And here you have an expression that does not depend on psi, depends only on theta, right? And actually shows you that you have a difference between forward scattering, that is smaller, and backward scattering. So particles tend to be back scattered, and only some of them go through the sample, right? And there is no dependence with the azimuthal angles, and that will be just the situation, right? In the case of X-ray diffraction, actually, we have to deal not with a simple expression, but we have to deal with this FQ, the form factor, where the incident wavelength interacts with all the electrons corresponding to the atom with some over n. So this will be the position of atom n, and this will be the position of the electrons, right? So this is a complicated expression that's actually some sort of Fourier transform. You can calculate this using quantum mechanics if you know the electron density. That's nothing but the Fourier transform of the electron density, so you could do a serious calculation for an atom and calculate that. But from a practical standpoint, you end up with a series of Gaussian functions like that, where all these constants are tabulated. And here, in the NIST page, is where you can find all these constants and construct the form factors for any atom. Recall, that's something very important in difference in X-rays with respect to neutrons. Cations and anions have different form factors. So in these tables, you will find, for instance, the form factor for calcium atom and for calcium 2+. Has 2 electrons less, 2 sources of the scattering less, right? So, so far so good as this basic stuff. And now let's try to go to where we left yesterday. So here we will take a look at what is the Fermi pseudopotential for a sample with multiple scatterers. And from there, we will actually talk about the static structure factor, that is the quantity of interest, right? We will see how is the scattering by a crystal, and then we will move from ordered systems to disordered systems. Finally, go into mixtures, molecular fluids, and trying to deal with mixtures and molecular fluids, see how we can handle them. We will talk a little bit about isotopic substitution that only applies to neutron scattering and to contrast matching, right? All these problems then, we will be connected with thermodynamics. This is what Marcia told you about. We will be connecting the structure factor with thermodynamic properties. Consider the structure factor as a response function, which is important in linear theory, and a linear response theory. And how is the structure factor in multi-component systems, which is a little bit tricky, right? And then trying to go back from structure factor into, which is in Fourier space, to real space, to things we can actually handle. We will talk a little bit about reverse Monte Carlo and other inverse techniques. These techniques that bring us all this information that is in Fourier space back to real space, right? The simplest thing is just Fourier transformations, but we cannot always do that for all types of samples, right? Try to move up here, because otherwise. Well, as I already mentioned, when you have a single scatterer, we start with a plane wave, that is this thing, this wave front that you can see here. You hit the scatterer, and once you hit the scatterer, you get a set of spherical waves, right? That's the result of the scattering. They have different intensities depending on direction, and the variation of this intensity depends obviously on the scattering potential. The scattering potential can be radial. Even if it is radial, it will have, you will see that it has an effect, as we have seen for the Yukawa case, that it's different depending on the theta angle. But the scattering potential could have also form, actually, if you have scatterers that are not simply spherical. But the case of interest for us is when we have multiple scatterers. When we have multiple scatterers, each one of these scatterers is the source of a spherical wave, and they produce interference, right? Because they cannot be distinguished one from another. Remember, coherent scattering. We are talking about coherent scattering. So we get constructed interference, and this constructed interference will give us information about correlations between all the scatterers. Okay. Let's see. Let's start with how do we sample this microscopic structure? First with neutrons, right? In the case of neutrons, they have a relatively small size. they typically have a wavelength. They are much smaller than the wavelength, the incident wavelength, the scatter sites. And this is the size we're dealing with. So something that is below 1 angstrom. And the scatter potential using the Fermi approximation can be considered just simply the summation of all the scattering sites. Recall that they are assumed to be delta functions. That is just point potentials. Each of them is source of a potential. So the details of V of R are really unimportant. The only important thing is just their position, right? And this is what constitutes the Fermi pseudopotential, right? Let's see what happens. We assume this Born approximation, they only scatter once. That means that if a neutron hits one of the atoms and gets scattered, it would not hit another. Well, this is very much of an assumption, right? And actually, in experiments, you have to correct for multiple scattering. In any case, you see here, that's the effect, is that you have a scatterer here with the incident light, comes here with a phase, and this other scatterer, also the spherical wave, comes with a different wavelength, right? With a different amplitude. Right. You have to add all these amplitudes because you cannot distinguish one from the other. And the intensity, which is proportional to this wave function squared, is just this connection that has these terms. These terms are individual terms, are single particle terms, and the cross terms that inform about correlations. Recall that these terms are not existent when you have incoherent scattering, and you only have information, single particle information. All right. With this like that, we express the potential in this wave. We put it here, and we have the differential cross-section as this summation squared with all these terms, where we have applied here Born approximation. Then we will have completely separate magnetic and structural diffraction. That will be completely different because their averages will be separated. So spin variables and particle positions are uncorrelated, right? So this is the key equation for scattering in neutrons. Now what happens? We have some sort of disorder because imagine that you do a scattering experiment with a simple gas like argon. If you get standard commercial argon and you don't want to pay a lot, argon is not just a single isotope. You look at the tables, argon, regular argon, has a composition that is 99.6% argon-40 plus approximately 0.3% argon-36 plus a little bit of argon-38. And this composition, it's spatially disordered. So actually, when you talk about the scattering length, you will talk about an average scattering length because you don't know exactly which argon atom you are hitting, right? So that's the reason why you really have to express this specific, this goes too fast. No. Right. You have to express this specific BI for a single atom as an average. This average would be, for argon, for instance, this quantity, 1.9, right? And a deviation from this average, a fluctuation. When you multiply two terms, you can end up with this. In the case of I different from J, recall this average, it's equal to 0 because there's no correlation between the different isotopes, this fluctuation. So you get this term, that's the average squared, and for this term you get this, and for this term you get this, right? When you take this into account, in a single component case, you end up with this expression. Recall, this is a single component case. This is the average B, that is the one you get in the table if you do not distinguish. If you use a specific isotope, you actually have to use that value. That would not be an average, but in this case, it's just an average. You can get it out because it's just that term. Here we have expanded the product. That means this exponential that we have here. If you just multiply it, take into account this is a modulus because this is a complex. So you multiply 1 by its conjugate. The fact that you multiply 1 by its conjugate results, and that here you have Q times the difference between the positions. That's because it's not simply you square the terms. You multiply 1 and the conjugate, right? And this is very interesting because this will be the coherent structure factor and represents correlations between particles. Now you see the particles. Before, the previous expression looked like it was just the sum of single particle contributions. But because you are using the modulus there of a complex number, you end up with something that is the Fourier transform of the pair distribution function. We will see that later, right? And you get an extra term. An extra term that is the result of the fact that you do not have a pure sample, isotopic sample. You have a mixture. So you get this fluctuation term, and this fluctuation term will give you a background. Depending on the spread of the mixture, of how the many different types of isotopes you have, this fluctuation will be bigger or smaller, right? If you have only one single term, that goes to 0, you have no background. In a real system, unless you pay for pure isotopic sample, which is sometimes expensive, you will get some contribution as a background incoherent scattering, right? Now, if you have mixtures with different components, then you have to be careful with that and treat explicitly. You cannot simply get this term out of the summation because you will have inside here the average of By times the average of B2. For instance, a mixture of argon and xenon or neon. Well, you will have a mixture of isotopes of both things, and you will be dealing with the averages inside the summation, right? You cannot get it out. Now, if you have spins, that's the point. You have here, you combine the spins. Some of the spins, neutron is a 1/2 spin particle, like the electron. So if it interacts with atoms that are not spinless, it will have different scattering length with respect to spin up neutrons and spin down neutrons. You can actually use this to do magnetic studies using polarization of the neutron spin beam, right? So sometimes it's a pain, sometimes it's a blessing again, right? So with this you can build, combining the different values of the spin of the I. So the larger the nuclear spin, the more values you will have to combine, right? You end up with 2 different scattering lengths for coherent and incoherent scattering. And this is a table we just already commented on yesterday. Just recall 2 important things. Hydrogen, regular hydrogen, as it appears in regular water, for instance, has a huge incoherent scattering length. So trying to do neutron scattering on real water, on common water, is useless because incoherent scattering will mask everything. So for these experiments, you will have to use deuterated water that has a much lower incoherent scattering and a higher coherent scattering, right? You have elements like vanadium and aluminum that, due to this 0 incoherent scattering or 0 coherent scattering, are good for windows or are good for containers, right? This is very good if you do dynamics, because it will not affect the dynamic scattering. And this is very good if you do structural analysis, because it will not affect the elastic scattering. Okay, back to the structure factor. So typically, by definition, we define the structure factor as this term. The average of P squared is the differential cross-section times the number of particles. With this definition, you end up with this, which can be expressed in terms of correlations in this way, simply calculating this modulus and squaring it. Now, computational detail that has to be taken into account if you are doing programming to calculate structure factors. This operation is order n, so increases with the number of atoms you are considering linearly. This operation that gives the same result is order n squared, right? So this is very important. There is a caveat here, however. If you use this expression to calculate the scattering, the structure factor, if you have a mixture, you only be able to calculate directly using this expression the total structure factor, that means that due to all components, disregarding the species, or those contributions that come directly from one component or the another. For instance, if you have argon, a mixture argon-xenon, you will get the structure factor of argon-argon correlations, the structure factor of neon-neon correlations, and the total structure factor. But you will not get the cross correlations. You will not get the structure factor due to correlations between argon atoms and neon atoms. In the case of binary mixtures, you can use the trick of subtracting. So you have two components, you have the total, the cross correlation, you just simply get by subtraction. So that's simple in the case of binary mixtures. If you have three components or more, the trick doesn't work. So you are stuck with that. If you want to separate components, you have to go back to the order n squared expression. So this is just a computational detail. And then a tricky thing about this expression that sometimes is confusing. Very many times, if you look at, for instance, a single component system, the structure factor typically for large Q goes to 1. 1 means uncorrelated particles for very low Q. That means very small r. There's no correlations for very, very small r. Now, in mixtures, by the fact that you are using this definition, oops, this goes too fast. The limit when Q goes to infinity is this quotient. Obviously, if you have a single component, this is just 1, right? But if you have multiple components, it will not be 1. And this is due to this definition, right? So you have to be careful with this type of things. So take note on these details because it might lead to certain confusion, right? Now, let's see what happens with a crystal, right? In crystals, you have order positions, right? And you have layers. So you have this incident wavelength here, like that, which is in phase, and you have this other incident wavelength that has a different path. And for the reason of this different path, there will be interference. But the difference with respect to a disordered system is that this difference in path is just the same for all the scatterers, or they are just multiple of that, right? As a result of that, you will have diffractions that will satisfy this rule, and you will get peaks, marked peaks. These are called the Bragg peaks. And this is because the system is ordered, right? And results from the fact that you will always have a uniform distance between the two Bragg peaks, right? Between the two atoms in different layers. So there is regularity. That's a simple case. It will be something like a cubic lattice. But similar things will happen for other lattices. Regularity will be reflected in these Bragg peaks and infinite range correlations. Now,
and if I have like a liquid crystal that is ordered in one direction, means that I have to do the scattering, rotating.
A liquid crystal that is let me remember, liquid crystals will give you a diffuse scattering because it's positionally disordered. You will have to check for other properties to detect that for instance, that there is anisotropy. You will have to check, for instance, by the electric constant will be different depending on the direction. And the response, because the response to the field will be different depending on how you hit the liquid crystal. So yeah, that's completely different. But as far as X-rays, for instance, it's a liquid. Okay? So first type of diffraction that was done on crystals was called a single crystal diffraction. And this was very useful, and it is still very useful to determine the precise positions of atoms in a lattice. Single crystal diffraction gives you this. This is a diffraction pattern. So you get precise spots in the receptor, in the detector. So you have here, that's a standard wave of doing things in the old times. You have this rotating ring. You have the crystal here. You have the X-ray being hit in the crystal in a certain direction. And here you collect the diffracted photons. This is a photosensitive film in former times. Now it's a CCR camera. So, and you get bright spots, order bright spots. So that's precise, the precise result that you have a diffraction from another crystal, right? Depending on the direction, you will get different diffraction patterns. And thanks to that, you can reconstruct from Fourier space, because what you see here is Fourier space, as is the structure factor that depends on angles. That's in Fourier space. You rotate the crystal, and you can get the information when you invert that, what they call the phase problem, of where are all the atoms in the crystal. These days, I mean, most of the standard crystals, or very many of them, are easily characterized. The real pain these days is doing this thing on proteins. So one of the large areas of research in structural biology these days is trying to turn proteins into crystals. There are tiny crystals, of course, because it's very difficult to get them. And then you take them to a synchrotron, because the sample is very small, so you can't do that on the lab with the protein. And the synchrotron has a very high flux, and then you just analyze what is the structure, and then you can get a precise description that goes into this protein database bank. Problem: proteins of interest to us are in solution. Who knows if the ones that are in the crystal have the same structure? So this is the big fight between the NMR people and the people doing crystallography in proteins, because in NMR you do solution. The problem is in NMR you can only do small proteins. So that's sort of the pain you have to live with. Cryomicroscopy might help in that respect, because you might be able to freeze the proteins in natural state. But I'm not too sure how this works. So, and in the case of cryomicroscopy is basically the same idea. You can actually rotate the crystal, and you do, instead of using X-rays, you use an electron beam. The only problem, so to speak, is that after you examine the sample, you destroy the sample, right? Because the energy of the electrons is really huge. Okay, so how is the structure factor of crystal? In principle, since the positions of the atoms are fixed, that's the idea we all have about the crystal, that all positions are fixed in space, we should get infinitely narrow lines. But, well, that is not the case. And that is not the case because the crystal is at a finite temperature. It's vibrating. Even if we have a very low temperature, there is always some vibration. That means that this expression that we have for the structure factor, we can actually manipulate and put here the equilibrium positions of the crystal. That will be the positions of the crystal at 0 Kelvin, right? Where it's actually, there is no movement at all. And some term, it actually has a Q² term, and this is the average amplitude of the vibration of the atoms. Assuming that they are all the same, this is a simple case, all same atoms, you can, and a very uniform lattice, all would vibrate in the average in the same way. So you end up with this thing, and this thing is a very important quantity that is called the Debye-Waller factor. That is the correction for temperature, right? This term typically depends on T². The lower the T, the smaller this factor, right? So this is very important. If you want to get a very accurate measurement, you should lower the temperature to have less, and you will have narrower peaks, right? If you have different atoms, then you have to fool around, or a lattice where atoms are not chemically equivalent. That is, for instance, in one position, one atom is surrounded by 8, and in another position, an atom is surrounded by 4. That's typically in, say, for instance, an FCC lattice. You have 8-fold coordinated and 4-fold coordinated sites. You have to take into account that several Debye-Waller factors will appear, or you will have an average more or less complex. The easiest thing is to do some fitting and forget about it, right? That's when you don't know how to handle things, you just fit. Powder diffraction. This is the essential technique that you use for characterization of materials. So when you don't know when something is, there are a lot of tests that you can do. But if you have something that is a crystal, the first thing you do is just you simply grind it completely down to just fine dust, compact it into a pill, and do diffraction. When you do that, you end up with microcrystals in all possible orientations, not a single crystal. So your incident beam will hit one crystal in one orientation, another in a different orientation. That means that the effect of having powder diffraction is that you will have an orientational average, right? So forget about moving your sample like you did with the crystal, because whatever you do with the sample, you will get the same effect, right? And you have this funny thing. You have rings. When you have rings in the diffraction instead of spots, the first thing that comes to your mind says, gosh, the system is disordered because you have rings. But then you look at the intensity of the rings, and the first thing you see is that the intensity of the rings does not decrease with Q. It's very large for all Qs. And then you have to suspect that here you have long-range order. So this disorder you see is the disorder of the microcrystals, right? The differential cross-section now is a little bit more tricky because you only have diffraction for these wave vectors that actually hit the wave vectors compatible with the lattice cell. That is this tau crystal. Every cell has a basic unit vectors, and these unit vectors are the ones that will produce the diffraction, right? So that's the reason for this term, that you only sum over the wave vectors compatible with the cell. And you have this delta Q, because all other Qs will be canceled. And this is why you have these huge peaks and 0, 0, 0. When we go to a liquid, you will see that this is not happening, that not all Qs are canceled, because you have disorder, you have a scattering of all wave numbers, right? But in the crystal, you see that, even if the crystal is, in principle, disorder. But it's disorder at the mesoscopic level, not at the nanoscopic level, or microscopic.
And the double peak is internal structure?
That's internal structure. That's simply sometimes because there are diffractions from some plane that are very close to each other. So that's the structure of all the possible refractions that you have. The simpler the lattice, if you have a simple cubic lattice, you just get one peak practically. So But if you have a very complex material, you have thousands of peaks. This is a signature of the material. So you know, for instance, if you study graphene, you have a very marked peak that marks the distance between the layers in graphene. So if you are studying carbon material and you get a peak at that position, says, gosh, I have here graphene layers. So this is one of the standard analytic techniques together with infrared, Raman spectroscopy. It's always the same trick. You go to the tables, look where the peaks are supposed to be in known substances, and know if they fit here. If you have a mixture of substance, you will probably see peaks from all the substance, right?
Can you use it for porous materials?
Yeah. For porous materials, you will get something tricky that is a very low Q. You will have a huge peak. That follows a law that is called the Perron's law, and with that you can get an estimate of the pore size. I will talk later about colloidal materials. In colloidal materials, you also have that. You have a huge peak, a huge pre-peak that signals the formation of aggregates. Voids are just completely similar to aggregates that imply correlations. So I'll give you an example later where you see how the structures or the structure factor of a system with voids, with bubbles, and a system with globular aggregates is practically the same because of that. Because you see correlations, but sometimes these correlations are correlations between empty spaces. Also, the width of the peaks not only is determined by thermal movement, that's the Weierwälder factor, and a way to kill the Weierwälder factor is to use liquid nitrogen. If you can, you put liquid nitrogen around the sample, and that's it, you cool it. There are other ways to cool more sophisticated, and you can cool it down to 0 key, and you kill the Weierwälder. But there is something you have to live with, and it's the instrument resolution. The instruments do not have infinite resolution, right? So these two effects are modeled what is called a pseudo-Voigt function. Pseudo-Voigt is called pseudo-Voigt because Voigt functions typically are convolutions of two functions, a Lorentzian and a Gaussian. Well, the Gaussian, you know already where it's coming from, the Weierwälder, right? We could see that it's, with respect to Q, it's just a Gaussian. And the Lorentzian comes from the instrument resolution. And this is something you have to estimate. With known samples, you do measurements with your experiment, you lower your temperature, and you can actually extrapolate until you get rid of the Weierwälder factor, and end up with the width introduced by your experiment resolution. So that corrects that this delta Q minus Q naught that we had here, this would cause infinitely narrow peaks. Because you don't have that, you have this width of the peaks due to this term. So actually, strictly, when you do strict programming, this is what you have to put there in the summation, right? Another consequence of powder diffraction is what is called diffuse scattering, right? When you have disorder, and this disorder can be either positional or substitutional. Positional disorder is that crystals, we are used to treat crystals as perfect entities, but that's far from true. The most perfect crystal typically has defects, and these defects are vacancies, places where one should expect an atom to be, and the atom is absent, right? And you have also interstitials. That is an atom that is in the wrong position, gets in the middle there, and you can calculate the higher the temperature, the larger the number of defects that you have in your crystal. Defects, again, has a downside and a positive side. Downside is that crystal, some of the properties will be poor because of that, but sometimes, for instance, when you do with semiconductors, Well, you might improve, depending on the number of defects, the property of the semiconductor. So you have to fiddle around with these things. But from the point of view of the scattering, they imply that they have disorder, right? Now, you also can have substitutional disorder. Substitutional disorder is the fact that if you have, for instance, brass, which is an alloy made of copper and zinc are not in fixed positions. Sometimes, this is typical from metals, because metals are very special. I mean, if you have sodium chloride and you look at the lattice, sodium has perfectly defined positions, chlorine has perfectly defined positions, but well, there might be vacancies and there may be defects. But if you have this thing, or you have a solution of mercury and gold, mercury has the funny habit of dissolving gold. That's one of the reasons why it's used a lot to extract gold from material, particularly in the Andes. And what happens is that in a metal you have cations and you have the electron cloud. So it's very easy for cations to move around and to have, particularly if they have similar sizes, which is usually the case. So they may occupy randomly defined positions, and you cannot define where they are. Some of the systems, like semi-metals, for instance, if you do an alloy of selenium and tellurium, which is not, they are not strictly metals, they are semi-metals, both behave as semiconductors. Same thing happens, because they are also very similar in that respect. So when you have that, what happens is that you will have diffraction peaks, right? But then you have the shape that comes from the disorder substitution. Because even if they are disordered, there are correlations. Obviously, they are not completely random, because the interaction between gold and mercury is different from the cross interactions. So they dissolve in this sort of homogeneous mixtures, but they have some underlying structure. It's like as if they were in the liquid. If you melt both materials, they do not separate. They are completely molten, and they have certain structure, right? The same thing happens here in the solid. So that's a very tricky thing. Silver iodine is even more interesting because it's a solid, but silver can move in the lattice. So that makes things even funnier. And it actually can be used as conducting material because of the movement of the cations. It is very unusual. Now it's not that fashionable anymore, but it used to be very fashionable some 20 years ago. But the result of all these things is that you end up with this very complicated structure, and that it's actually the convolution of the diffraction of the lattice itself and the internal structure of the alloy or the positional disorder. And this is really difficult to model. I mean, from the crystallographic point of view, it's impossible. Using the standard crystallographic techniques, there's nothing you can do because there's disorder. You can't do crystal repositioning or reorientation. So you need techniques like this one I mentioned, that is a reverse Monte Carlo. Or if the material is sufficiently known to have force field well-defined, you can do simulation and pray that it actually is able to reproduce the behavior of the material.
Keep increasing Q, you get, the background oscillation.
Yeah, it's like a liquid.
Yeah, exactly.
Because if it's the structure of a liquid inside a solid. So that's the funny thing of this material, that you actually have like a convolution of a liquid and a solid. There are correlations, but they are not sufficient to place the atoms of each substance, each element in fixed positions.
How fast are these atoms that move?
Sorry?
How fast are these atoms? Like they move?
No, in this case, they do not move. I mean, if you look at brass, they don't move. I mean, they move if they are in the liquid phase. But once you, I mean, to make the alloy, you have to melt them. Once you freeze them, that's it. Everything is frozen at the position they had in the liquid. That's it. The case where they move, it's the one I mentioned, this silver iodine. In silver iodine, they actually move. And they actually move relatively fast, because otherwise, I can't give you a number, not to say anything stupid. But I remember that they were considering actually using it as a conductor. So that means that mobility should be relatively high. Sorry? If you lower the temperature sufficiently enough, they stop moving, obviously, right? No. They move through holes in the network and exchange. Now, there are holes in the network that move to a place, and so the network is, the lattice is sort of full of holes. So it has plenty of space, and that's the reason why the cations can move. The iodine is a big atom, and they can actually move inside. So that's a tricky thing. I think they would used to be called conducting solids. So if you take a look at the Google, there's papers on silver iodine will show up, right? It will give you all the information. I mean, I think it's a curiosity. From the technical point of view, my impression is that no more research has been done on similar systems. But similar thing has been done in conducting polymers or whatever. So, or now there's a lot of work on electrolyte gels, which are ionic liquids that end up like they are very dense and they end up in a gel, but the ions, so they are disordered, but they have very little diffusivity, but some of the ions can move relatively fast and act as conducting. So they want to use these electrolyte gels for batteries because they are safer. Not being liquid, they are safer. So there's lots of research there. I don't know if they will reach a point where you will have them in your cell phone. We'll see. Okay. Let's try to connect this with something that you are used to, those of you who have been working a little bit in statistical physics. That's the standard definition of density of a fluid, technical definition, so to speak. So it's you sum up of all positions, and it's a delta R, assuming that particles are point particles, right? And this you divide by the volume. And the Fourier transform of this gives you the Fourier transform density functional, right? The integral of this quantity gives you n, the number of particles, right? And if you express S of Q in this way, here, you expand this thing and you end up with the product of two densities, the convolution of two densities, sorry, right? This quantity here you look at that, with this definition like that, is the pair distribution function, right? Because they integrate, you have the two deltas. That means you are correlating positions of particles in a fluid, of two different particles, right? When you put that in that expression, you get the connection between the structure factor. Here, forget about scattering factors. This is just theory of fluids. Fourier transform of the G of R minus 1, right? That's the total correlation function, plus a term that represents the forward scattering. That's what goes in the forward direction, that we know that you get. This is precisely, if we go back here, well, here you can already see it. This huge bright dot in the middle is forward scattering, right? I think it's Let's take a 10-minute break, right? Okay, so we were just at this point talking about the GFR and the forward scattering. Right. Let's go to this other matter, liquids. Right? You have the simplest case of liquid argon. That's the standard thing. It's a Lennard-Jones liquid, the standard Lennard-Jones liquid. You can correct, if you are very fussy about things, you can add three body forces to get some properties exactly like the experimental one. But for most things, simple Lennard-Jones fits the behavior of liquid argon. And you can easily invert using Fourier inversion and get the GFR, which has this as the structure of the liquid. Here we have a little bit more complicated system. That's selenium. Selenium is a solid that is formed by, in the lattice, parallel chains, because it likes to have coordination too. If you look at the electronic structure of selenium, you would see why it likes to form chains, right? And when you melt it, for a long range of temperatures, it preserves the structure of the chains. And this is one of the funny things about selenium, that is in the solid phase is a semiconductor, and when you go to the liquid phase, it remains as a liquid semiconductor, because it retains the structure of the chains. If you further heat it, obviously you break the chains and you end up with a highly coordinated liquid. And here you have the structure of the liquid selenium. There is a feature, and here is inversion, so of the GFR. If you actually integrate the GFR, you know, if you integrate the GFR in three-dimensional space, that is taking into account that the differential of volume is 4 pi r squared differential of r, and multiply by the density of the liquid, here you end up with a value of 2. That means this integration up to this point is precisely the neighbors that you have for a single atom in selenium, and since it forms chains, you have 2 neighbors. That's the reason why this peak is so narrow and so deep, the valley here, compared with that of argon, which typically has between 6 and 8 neighbors. That's the standard for a liquid. There is a feature in selenium that is worth spending a few minutes, and it's this thing. See, you have here a first peak of diffraction. The first peak in the diffraction typically comes from the distance intermediate correlations, right? The phase comes from the separation between nearest neighbors. I mean, if you take a look at, well, we will see it later when we talk about diatomics. If you have a fixed distance, if everything was frozen in space, you will have a delta function of r minus this distance. If you Fourier transform that, you end up with a function that is sine q times the distance divided by r. That is an oscillating and decaying function. This oscillating and decaying function has the period connected with this correlation distance between the nearest neighbors, right? And the first peaks are intermediate correlations. The interesting thing in selenium is that you have a pre-peak at relatively small wave numbers. These pre-peaks are indications of the existence of supramolecular structures, because they imply, recall that Fourier space is the inverse of real space. So if you have a peak here, that means that you have correlations at 2 pi divided by q, by this q. Since this q is very small, that means sort of long-range correlations. What type of long-range correlations do you have in selenium? Correlations between chains. Chains are entities, separate entities. And the distance between chains marks precisely the position of this peak. So many polymers and many systems will show peaks of this type. For other materials, like colloidal materials, we will see later, you have pre-peaks that are much higher, or you even almost diverging pre-peaks, right? Back again to what I mentioned. This is a system that is an example of, well, a class of potentials that has been very much studied for the last 20, 30 years. Our potentials are called short-range attractive, long-range repulsive. What do these potentials come from? Well, if you think of a colloidal particle, colloidal particles are typically very big particles. Sometimes they are charged on the surface, right? And you have a screening that comes from an electrolyte that is dissolved in the water in which you have these colloids. So you have a long-range repulsion that comes from the Coulomb term. You have a Coulomb term that is a repulsion between the two colloidal particles. It is a screen Coulomb because you have ions there. A screen Coulomb is actually a Yukawa term, the one we saw before. That means has the same expression as the Coulomb term times an exponential. And the exponential is modulated with something that depends on the concentration of ions. The higher the concentration of ions, the faster the Yukawa term decays. If you have a dilute concentration, you have a very long-range interaction, right? So there you have the source of the repulsion. Where does the attraction comes from? Well, the attraction comes typically from an effect that is called the depletion effect. The depletion effect is something that happens when you have large particles together with small particles. If you have two large particles together, they leave more room to small particles. That's easy to see if you separate them completely. On one side, large particles, on the other side, small particles. That's the perfect solution. If you have, for instance, in cereal boxes, sometimes when you have small cereals with big cereals, you see that the small ones go to the bottom. They separate. Precisely because it's better for the distribution of space. They occupy less room if you have separated phases. Well, this tendency of the big particles to be together, I mean, it's how to speak, it's an effective interaction. It's an interaction that comes as a result of volume effects. It's not that there is something really attracting, but it has the effect of an attraction. And it is obviously short-ranged. If particles are very much separated, if you have a very dilute colloid, you will have no depletion whatsoever. But when you have a certain concentration, you have this effect, right? So it's short-ranged. When you have a certain combination of temperature, density, and parameters of the potential, what happens is that these colloidal particles concentrate in aggregates, in clusters. Clusters that, in this particular case, have sort of spherical-like shape. Not completely, and they have a certain dispersion in sizes, right? And they are stable, right? If you did not have a repulsion, the system would collapse, and it would phase separate. That is what happened in a regular liquid. When you are in the vapor, you start to have droplets. Droplets are larger, smaller, but sooner big droplets start to absorb small droplets, and it separates in a single phase. Here, why this does not happen? Because you have repulsion. So these droplets here repels the small droplets. And that's the reason why they do not coalesce into a single phase, right? If you look at the structure factor, you have a relatively high peak here, K naught, which is a very, very low wave number, right? Look at the G of R. The G of R has this structure. This structure corresponds to the internal structure of the droplet, which is a liquid. Goes up to 6 sigma, and then it dies out. That is telling you that the size of these particles is around 6 molecular diameters. And then you have a peak here. And this peak here corresponds to the separation between droplets. I mean, if you forget about that, it's like you have a liquid with an oscillation that peaks precisely at this point. And this point is 2 pi divided by k naught. So correlations between the droplets, between the aggregates, display as a pre-peak in the structure factor. And this is key in soft matter. Long-range repulsion. But you can have this effect in many things like micellar systems. You have amphiphilic materials, detergents, surfactants. They aggregate and you will see the same thing. The only reason that, the only difference is what is the source of the aggregation. In this case, the aggregation comes from the attractive force, and the stability of the aggregates comes from the repulsion. But anyway, these SAR potentials have to be thought of as effective. If you want to go to a real system, you have to check for a colloid or a surfactant, right? Well, the size, that's an interesting question. The size of the aggregation if you look at the potential, I didn't want to complicate things too much, but the potential is something like this. So the potential here has an attractive well, and here is repulsive. At this point, you have F and this is approximately R naught. Is the point of balance between attraction and repulsion. So that defines the size of the aggregate. Now, this is for relatively low density. If you increase the density, there you have. That's a lamellar phase. That's a phase that spans the entire, in this case, entire system, and forms lamellars. Lamellar, this structure that you can see in many materials, where you have the aggregate, you have the solvent, aggregate, solvent, and here, look, the structure is very, very similar. That's one of the tricky things. One has to be very careful when analyzing results from diffraction, because you only get pair structure. And since you only get pair structure, you get this structure factor, which peaks at K naught, has a maximum here, has the maximum here. This is the intra-layer liquid structure corresponding to each of these layers. It has a maximum here. Look, it's identical. But the system is completely different. So you have to be careful with the interpretation of your results. You have to use additional techniques because you only get pair correlations. And pair correlations are very limited in many respects, right? There are other properties, obviously. If you look for the dynamics here is completely different, obviously. It's not the same thing to have clusters moving. So you do, for instance, dynamic like scattering, you will see something completely different here and in the other case. Because it's not the same thing trying to move a lamella that will practically not move as collective movement than trying to move a cluster that will move, right? But from the static point of view, you are a little bit stuck, right? See that concentration here is, well, this is in reduced units. Here is 0.114, and here is just more or less the double. We go further, double again. And here we get something that is called the bubble phase. Same thing, but there you have bubbles, right? It's like in sponge material. You freeze it, and you will get a sponge material or a porous material. So that's a way to synthesize this type of materials. Look at the structure factor. It looks very similar. But now the GFR is different. And it's different because the peak here is missing. Why is it missing? Because R0 represents correlations between the holes. And you don't have particles in the holes. So that's the reason why you don't have that peak. But still, the structure factor sees the correlation. And sees the correlation, and that's the reason why normally you can see this type of structure factor in porous materials. Only that in many porous materials, you are not able to reach to the point where this falls. So you don't get to that very small wave numbers. So in most porous materials, you only see the structure factor going up and up and up and up to this point. And you don't see the going down. I mean, you could use it if you use a technique that is called ultra small neutron scattering, USNS, which is extremely expensive if you don't do that for something. I mean, if you are not going to cure cancer, forget it. They will not grant you time for that. But you know that it's like that you don't see it because you haven't reached sufficiently small wave numbers. That's where simulation can help you, because you can do the simulation for the porous material, construct the structure, perform the calculation, and then you see how it goes down, right? So the law that I mentioned that gives you the size and estimate of the porosity applies to this ascending part of the peak. That's Poros's law, right?
But if I calculate from the simulation the GOR, I don't get, I get this.
Yeah. You get that there is no peak.
But then, if I Fourier transform the GOR, I get this CO2.
Right.
You get it?
You get it. This is done numerically. Yeah, this has been done numerically. This is not an experiment. This is a simulation. Periodic boundary conditions, yeah, obviously. Yeah, the system percolates. The system percolates, right? So you have boxes of the same size all over, yeah. This also percolates to a certain extent. No, not really, but it's on the verge of percolation. You see there is some places, if you increase a little bit the density, probably the lamellas will just merge and it will percolate, right? So this is in between, but it still is not forming bubble phases. So I just want to mention something that is interesting. I didn't put the transparency here, the slide here, but some colleagues in La Plata with whom I worked for quite some time, Ariel Meira and Victor Kutz, they actually analyzed these patterns, and they made they studied some Google pictures from La Pampa and from some places in Africa, and it turns out that these patterns are displayed by vegetation in areas where they have to fight for resources. And then you will ask, what's the SAL interaction there? Well, it's very easy to understand if you think, for instance, of an African acacia. Acacias in Africa, African acacias have very wide canopy. The top of the tree, the branches are wide and flat. And they try to sort of get together to produce as much shade as possible to prevent evaporation, right? So that it's an incentive for them to gather together. But on the other hand, to take the most profit of the very little precipitation they have very wide and extensive roots and very flat. They do not go deep in the soil because there's nothing, so they go right in the surface. And obviously, they don't want to entangle their roots, so they try to stay as far apart as possible. There you have the repulsion. So you play a little bit with the density, and you see all these pictures in La Pampa. So I think it's a very interesting thing because it tells you that these simple, effective interactions are behind very many simple natural phenomena. Obviously, it comes a discussion that there is a simplification because you have to do some fitting. But it comes out, so it is there, and also it makes sense when you think about the natural phenomena. Only that you cannot deduce the interaction from first principles. But again, Lennard-Jones is hardly an interaction from first principles. The 1/R6 term is just a term that comes over due to the fluctuation of dipoles. So that's sort of first principles. But the repulsion is kind of arbitrary, and the rest you fit to get the best experimental results, right? And I think we just leave it now for now, and tomorrow a little bit more. Okay? Thank you.